The cosmic clock is ticking. A colossal shadow once dismissed as just another icy wanderer now hurtles toward Jupiter. It's an enigma named 3I Atlas, and its trajectory isn't random. It's a deliberate arrow aimed at Europa, Jupiter's icy moon, a world cradling an ocean twice the volume of Earth's. But what if this isn't a natural comet? What if humanity is merely a background player watching a package arrive that was never meant for us? What if this isn't just a visitor, but a delivery, a seed hurtling through the void, carrying not just elements, but the very blueprint of alien life, poised to ignite a new genesis in the frigid depths of another world? And what if one day that new life remembers where it came from, or where it was sent from? If you're as captivated by these cosmic puzzles as I am, consider subscribing so you can follow along as this story develops. Leave a comment telling me where you're watching from and what you think. Are we witnessing something unprecedented, or is there more to 3I Atlas than we're being told? Part 1, the Europa Shock Theory. A frozen world Europa orbits Jupiter in silent grandeur. Beneath a colossal crust of ancient ice, 15 kilometers thick lies an ocean. Not a mere lake, but an entire global sea dwarfing all of Earth's oceans combined. This titanic liquid realm, insulated from the sun's touch for billions of years, is kept from freezing solid by the relentless gravitational torment Jupiter inflicts on its moon. This is Europa, a pristine, dark and potentially vital laboratory. Now imagine something is hurtling directly for it. For the past year we've tracked 3I Atlas, the third confirmed interstellar visitor ever detected. It's not from our solar system, it's not bound by our sun's gravity. Its hyperbolic trajectory screams one word: visitor. Conventional wisdom once predicted it would simply pass by a cosmic tourist snapping photos and moving on after its closest approach to the sun in late October 2025. But conventional wisdom failed to account for the astonishing truth that unfolded next. 3I Atlas isn't leaving, not yet. Its path, when meticulously calculated, when orbital mechanics are plotted with agonizing precision, reveals a destination so shocking, scientists initially refused to say it aloud. This object is bending sharply toward Jupiter, toward the Jovian system, toward those icy moons hanging like frozen embryos in the lethal radiation belts, seemingly waiting for something to awaken them. Scientists must call it a comet. It has a coma. It outgases. On the surface, it behaves like every other dirty snowball we've catalogued. Yet imaging data from advanced space-based observatories tells a radically different story. Its jets, its anomalous composition, its peculiar behaviour under intense scrutiny. This is no ordinary comet doing ordinary comet things. This is something else entirely wearing a comet's disguise. Whispers, then louder conversations among researchers in hushed conference rooms are starting to use a different word. Not a visitor, not a tourist, but a delivery mechanism. What if Earth was never the target? What if we've been sitting here building our telescopes, convinced that any cosmic threat or gift would come for us, while all along the true destination was somewhere else? What if we're not the main character in this unfolding cosmic drama? What if we are merely background extras, a discarded prototype, a rough draft crumpled and tossed aside while the universe moved on to better things? The speculation intensifies around a chilling alignment. 3I Atlas's post-solar trajectory, when extended when you follow the gravitational breadcrumbs, points toward the Jovian system with unsettling precision. It's not a locked-in collision course, not a guaranteed impact, but it's close enough that the experts who model these things for a living are losing sleep. Europa sits out there, a pristine, almost sterile laboratory. No contamination from Earth. No billions of years of complex evolutionary baggage. Just clean ice, an unfathomable volume of clean water and energy from tidal flexing that could power chemistry we can't even imagine. If you were going to seed life somewhere, if you truly wanted a blank slate with all the right ingredients, you wouldn't pick Earth. Earth is too crowded, too messy. Earth already ran its experiment and produced, well, us. This is the shock theory. The deeply uncomfortable possibility that 3i Atlas isn't heading home, it's heading to work, a sophisticated delivery vehicle carrying something we barely understand to a location we've barely explored. And if that's true, if this hunk of ice and rock and whatever else is packed inside truly is steering toward Europa, then every assumption we've made about our place in the cosmos just became obsolete. We once believed first contact would be about us radio signals, little green visitors, some cosmic acknowledgement that Earth matters. But what if first contact is simply watching someone else receive a package we didn't order? What if we are just unwitting witnesses to a cosmic transaction that has nothing to do with us at all? Space agencies won't confirm it publicly. No official mission target. No statements about intentional steering. But the numbers don't lie, trajectories don't have agendas, and 3i Atlas is going somewhere specific. What comes next depends entirely on its payload. Is it biological, chemical, or something we don't even have words for yet? Is Europa's ocean about to receive the most pivotal delivery in the history of our solar system? Or worse, is Earth sitting here in the inner system about to become utterly irrelevant if it isn't already? This thought haunts scientists, not the mere possibility of alien life. We've made peace with that. But the possibility that we were considered and rejected. That Earth was evaluated, found wanting, and passed over for a better candidate. That's the existential wound that might never heal. To be ignored hurts more than to be destroyed. If 3i Atlas truly is a seed ship, if an intelligence calculated trajectories, packed payloads, and launched this artifact across light years with Europa as its ultimate destination, then what does that say about their assessment of Earth? Did they look at us and see a biosphere too volatile, too contaminated, too far down evolutionary paths that proved unuseful? Did they decide we were the beta test and now they are ready to launch the real product? These questions don't have comfortable answers, but they are coming because 3i Atlas is on its way. Part 2, the payload hypothesis. What exactly is the 3i Atlas carrying? If 3i Atlas is more than a random icy rock, if it's purposefully built, then its composition is paramount. What you pack into an interstellar vessel determines its fate upon arrival, and the chemistry we're seeing, it's making people deeply nervous. The James Webb Space Telescope has had its powerful eye on it, along with a coordinated network of ground-based observatories, all firing like a cosmic firing squad. What they found was a coma overwhelmingly dominated by carbon dioxide, not water. This CO2 to water vapor ratio is among the highest ever recorded in any comet studied. That's profoundly abnormal. Our solar system's comets are water-rich, essentially melting snowballs, with other elements mixed in. 3i Atlas is the inverse, a carbon dioxide factory with water as a mere side dish. Why is this critical? Because carbon dioxide, especially in combination with the other detected molecules, water vapor, carbon monoxide, carbonyl sulfide, water, ice grains, dust, tells a story of its incredibly long journey through the cosmos. The outer layers of its nucleus have likely been processed by galactic cosmic rays for untold eons. This relentless radiation bombardment over millions, possibly billions of years, creates exotic chemistry. It polymerizes organics building complex carbon chains. It generates precisely the kind of prebiotic gunk that under the right conditions could bootstrap into something far more interesting. This is where speculation veers into the wild, but it's informed speculation grounded in our understanding of radiation chemistry and molecular-level long-duration spaceflight. If you sought to send biological building blocks across interstellar distances, protection would be paramount. Carbon dioxide ice makes for an excellent radiation shield. A crust of polymerized organics painstakingly built up over millennia by cosmic ray exposure is even better. You would in essence freeze pack your precious payload in its own self-engineered protective shell, crafted by the physics of the universe rather than mechanical means. Some researchers are quietly exploring the possibility, a mere possibility as yet unconfirmed, that 3i Atlas could be carrying what they term cryovehicles. These are frozen capsules of complex organic chemistry, or even primitive cellular structures designed to survive the arduous journey, and activate only when conditions dramatically change. Imagine the trigger heat pressure liquid water, precisely the conditions you'd find if a comet-like object plunged into an icy moon's vast subsurface ocean. Think of it like boot code. Software is inert on a disk. It needs to be loaded into memory executed given the correct environment to run. What if 3i Atlas carries frozen instructions? Chemistry that only activates when it encounters the precise temperature, the perfect solvent, the correct energy gradients. A molecular domino chain waiting for its first push. This redefines everything. 3i Atlas ceases to be a mere geological curiosity and transforms into a potential seed ship. A vessel specifically designed, or at least profoundly conditioned, to carry the building blocks of life, or something like life, from one star system to another. The chemistry we're observing fits this profile with an unsettling exactness. High carbon dioxide, a radiation-processed crust, a volatile-rich interior, every component you'd need to keep a biological payload viable over deep time. The numbers are striking, revealing an anomaly that goes beyond mere variation. That CO2 to water ratio isn't just high, it's unprecedented. 3i Atlas stands almost in a category by itself. While some solar system comets show elevated carbon dioxide, nothing approaches these extreme levels. And when you combine this with the other detected molecules, the carbonyl sulfide, the complex organic signatures in the dust, you begin to construct a chemical profile that screams less random comet and more engineered package. Consider the radiation processing angle with utmost care. Galactic cosmic rays don't merely damage molecules, they forge new ones. High-energy particles violently slam into simple ices, carbon dioxide, water, methane, driving chemical reactions that would never occur otherwise. Over millions of years in interstellar space, this process accumulates. You get amino acids, nucleic bases, sugar precursors, all the fundamental molecular components that life, at least Earth life, requires to begin. If 3i Atlas has been travelling for 1 million years, 10 million or even longer, its outer crust could be a living library of prebiotic chemistry, a frozen catalogue of organic possibility primed for reactivation. However, let's be absolutely clear, there is no direct evidence of biological material, no DNA signatures, no confirmed cellular structures, no tiny frozen alien embryos floating within its core. All we have is chemistry that looks profoundly suspicious, if you are inclined to be suspicious, and trajectory data that points to a very, very specific location. The payload hypothesis remains precisely that, a hypothesis, a what-if scenario built on circumstantial evidence and a series of uncomfortable coincidences. But the very fact that it's even plausible, that the data allows for this interpretation, should command everyone's urgent attention. Because if 3i Atlas is carrying something, if it's truly more than just a comet, then what happens when it reaches its destination isn't merely an astronomical event. It's a biological one, perhaps even an intentional one. And if someone or something sent it, they had a reason. They meticulously picked a target. They carefully packed a payload. They launched it into the void and waited. For how long? Thousands of years, millions, does it even matter to beings who conceptualize time on such monumental scales? The cryovesical concept demands further attention, because it's rooted in real biochemistry. We know certain molecules can survive freezing. We know some primitive cells can enter dormancy states that endure for decades, even centuries. Tardigrades are a prime example. Bacterial spores exhibit similar resilience. The critical question is scale. Can you freeze complex organic structures or even simple protocells for millions of years and have them remain viable? Laboratory studies offer a tantalizing maybe, under precisely the right conditions, with the right protective mechanisms and with sufficient redundancy. If you were engineering a seed ship, you wouldn't send a single copy of your payload. You'd send billions, trillions, embedding them throughout the nucleus. Distributed storage, massive redundancy. Some would inevitably be destroyed by radiation. Some would degrade. But if even 0.01% survive, if even a handful of viable packages reach the target ocean and activate, that's enough. That is all you need. One successful replication event and you have seeded a world. We're about to find out what happens when the package arrives. Or perhaps unsettlingly, we're already finding out and we simply don't realise it yet. Part 3, directed panspermia models that match the data. Panspermia is an ancient idea, the notion that life or its fundamental building blocks can spread between worlds. Typically, we imagine this passively. A meteor impact on Mars blasts rock into space. Some of that rock over millions of years lands on Earth, perhaps carrying dormant microbes. Life spreads by cosmic billiards, by dumb luck. Directed panspermia is radically different. It is intentional. It requires intelligence. It demands planning. Someone somewhere makes a conscious decision to seed life on other worlds. Not by passively waiting for random impacts, but by engineering sophisticated delivery mechanisms, by calculating precise trajectories, by constructing vessels capable of surviving interstellar transit and delivering their payload to specific targets. 2 frameworks dominate the theoretical literature. Framework are scattershot seeding. Send thousands, perhaps millions of small objects in every conceivable direction. A few will hit habitable zones. Some will survive. Most will fail. It's a numbers game. Launch enough seeds and statistically some will take root. Framework B, targeted seeding. Meticulously calculate your trajectory. Utilize gravitational assists. Time your launch with astronomical precision. Deliver your payload to a specific moon, a specific ocean, a specific environment you have chosen, because it offers the absolute best chance of success. 3i Atlas. If it is indeed a seeder, fits Framework B perfectly. Its hyperbolic orbit is incredibly fast, and that is no accident. Shorter transit times mean drastically less exposure to destructive radiation, less time for delicate molecular structures to break down. Its anomalous chemical composition, particularly the radiation-processed crust, suggests it's engineered for ultimate durability for long-term survival. Exactly what you would want if you were sending something precious across light years of interstellar void. Natural comets in our solar system behave predictably. As they approach the sun, they heat up. Water sublimates. They develop characteristic tails, predictable symmetrical outgassing driven by solar radiation. 3i Atlas doesn't quite follow that script. The general patterns are there, but the intricate details are off. The composition skews inexplicably weird. Its behaviour under intense observation raises profound questions. Hypothesis: 3i Atlas is a stealth seeder camouflaged as a comet to avoid drawing attention. Or perhaps simply because that is the most efficient, durable and unremarkable form factor for an interstellar delivery vehicle, ice and rock. Simple, resilient and utterly unremarkable until you look closer. But inside a hardened payload protected by layers of cosmic ray-processed crust designed to survive entry into a subsurface ocean and precisely release its cargo. The delivery mechanics are the hardest part. It's not enough to simply send material. You must ensure it lands, that it survives the unimaginable forces of entry, and that it finds a hospitable environment. Europa's ice shell is dauntingly thick, 15 kilometers, perhaps even more. You would need either a very specific impact trajectory, one that penetrates the ice without vaporizing your precious payload, or you would need immense time. Slow, embedding a gradual descent through cracks and fissures over centuries. Either way, it's a colossal gamble. Consider the physics of impact. If 3i Atlas were to hit Europa, it would be travelling at tens of kilometers per second. That represents enormous kinetic energy, most of which would instantly convert to heat. Vaporization plasma, anything biological on the surface, would be sterilized in an instant. But what if the payload isn't on the surface? What if it's buried deep inside, protected by layers of ice and rock that ablate during impact, carrying the heat away, shielding the interior? What if the entire structure is designed to fragment upon entry, scattering pieces across the ice, some of which survive and eventually work their way down through cracks and melt zones slowly and inexorably? or perhaps impact isn't the delivery method at all. Perhaps 3I Atlas is designed for a near-miss, close approach that fragments it through the immense tidal forces from Jupiter's gravity. Pieces would scatter across Europa's orbital path. Over thousands of years, Europa would sweep them up. Soft landings, gentle accumulation, slow embedding into the ice. Eventually, on geological timescales, some of that material works its way to the ocean. Interface melts through and activates. The targeted seeding model demands solving enormous navigation challenges. You're launching from another star system millions of light years away. You have no real-time telemetry, no course corrections once you are in deep space. You calculate the trajectory before launch accounting for stellar motion, galactic rotation, gravitational perturbations from passing stars, and then you simply hope your math is good enough that millions of years later, your payload arrives precisely where you intended. That level of precision seems impossible, but maybe it's not about surgical precision, maybe it's about intelligent probability. You don't need to hit Europa exactly. You just need to get close enough to the Jovian system that gravitational capture or orbital resonance does the rest. You design your trajectory to intersect Jupiter's orbit. Let Jupiter's colossal gravity bend the path and accept whatever moon you end up near. Europa, Ganymede, Callisto, it doesn't fundamentally matter. They all possess subsurface oceans. They're all viable targets. Probabilistic success versus a single grand gamble. For the senders, this could be one shot among thousands. They may have seeded hundreds of star systems. Most fail. A few succeed. That's an acceptable ratio. The cost per seed is low enough, the potential payoff high enough that even a 1% success rate justifies the monumental investment. It's a gamble with potentially enormous payoff. If even a tiny fraction of your seeded material takes hold, if it finds the right chemical environment, the correct energy source, the precise conditions to replicate and evolve, then you have just established a foothold in a new biosphere. You have started something. A new branch on the tree of life, a colony, an experiment, a backup plan. For whoever sent it, this could be a legacy project, a long odds bet played across millions of years. They don't need immediate results. They might not even be around to witness the outcome. Perhaps their civilization collapsed. Perhaps they are long extinct. But the seed gets planted, the experiment begins, and if it works, if life takes root on Europa, then the gamble paid off. The ethical implications are staggering. If this model is real, if 3I Atlas is part of a deliberate seeding program, then we are witnesses to an act of cosmic-scale bioengineering, and we suddenly bear immense responsibilities. Do we interfere? Do we simply observe? Do we try to stop it? Do we even have the right to make that decision? International space law does not cover this. Planetary protection protocols assume human missions controlled scenarios. This is uncontrolled external. We didn't launch it. We cannot sterilize it. We cannot prevent it from doing whatever it's going to do. Our only option is to watch, to document, to prepare for consequences we cannot fully predict. These questions have no easy answers, but they are coming because 3I Atlas is on its way. And whether we're ready or not, whether we understand what's happening or not, the delivery proceeds. Part 4, the failed experiment angle. Is Earth a rejected trial? Imagine a workshop cosmic in scale where life engineers, beings with timescales utterly incomprehensible to us, meticulously seed worlds across the galaxy. They launch vessels, they wait, they observe the results. And when outcomes fail to match their expectations, when a biosphere develops in ways they didn't intend, they simply move on. They redirect their vast resources to new candidates, new blank slates, new attempts. What if Earth is one of those failures? What if we are the discarded prototype? This is not mainstream science. It's speculative astrobiology interwoven with existential horror. But it's a possibility worth considering, if only to grasp the full chilling implication of what 3I Atlas might truly represent. Because if Earth's own biosphere was itself seeded, if life here originated from some earlier Panspermia event, and if that event didn't produce the results the senders wanted, then it makes perfect chilling sense to try again elsewhere. Consider biochemical compatibility. Life on Earth exclusively uses left-handed amino acids and right-handed sugars. This is an arbitrary choice, a quirk of primordial chemistry, but once made, it is locked in. It forms the very bedrock of our molecular identity. What if Atlas baseline life, whatever that means, was intended to develop differently? Different chirality, different molecular pathways, different early branching decisions at the most fundamental chemical level. Earth could have diverged, evolved in directions the senders didn't anticipate or desire, rendering us biochemically incompatible with their grander designs. The molecular handedness question is far more profound than it sounds. There's no chemical reason why life should prefer left-handed amino acids. Right-handed versions function equally well in laboratory settings. But once a biosphere commits to one version, it's trapped. Everything builds on that foundation: enzymes, proteins, metabolic pathways. Metabolic. You cannot switch midway without catastrophic failure. If Earth life made that choice randomly, if it simply happened to pick left-handed amino acids during the earlier stages of chemical evolution, and if that choice was wrong according to whoever designed the seeding protocol, then we are fundamentally incompatible. We cannot be integrated into their larger project. We are a divergent branch that needs to be pruned, or more likely simply ignored. Or perhaps Earth was simply too volatile. Too many extinction events, too much surface chaos, asteroid impacts, supervolcano eruptions, violent climate swings, ice ages, mass die-offs every few 100 million years. Not a stable platform for the kind of long-term evolutionary project someone might have in mind. Count them the big 5 extinction events: Ordovician, Silurian, Late Devonian, Permian, Triassic, Jurassic, Cretaceous, Paleogene. Each one obliterated 50% or more of all species. The Permian event alone killed 96% of marine species. 96%. That is not a stable environment. That is a biological meat grinder. If you're running a long-term experiment, if you want to observe what happens when life evolves undisturbed for billions of years, Earth is simply the wrong laboratory. Too many variables, too many disruptions. You set up your initial conditions, you walk away, you return a billion years later, and everything's utterly different because an asteroid hit or a supervolcano exploded or the climate flipped. Europa offers something Earth doesn't: stability. A subsurface ocean insulated from every surface catastrophe imaginable. No asteroid impacts penetrating to the ocean floor. No atmospheric changes. No lethal UV radiation sterilizing the surface. Just kilometers of ice providing impenetrable protection with relentless tidal heating from Jupiter, providing a constant energy source. It's a controlled environment, a perfect lab, a place where you could run an experiment without external interference ruining it. The ice shell is key, 15 kilometers thick. That's absolute protection from everything. Asteroids cannot punch through. Radiation is absorbed. Solar flares are meaningless. The ocean underneath is isolated, stable, unchanging over billions of years, except for slow geological evolution. If you want to witness what life does given perfect conditions and unlimited time, that is your laboratory. If you're an alien bioengineer and you've just observed Earth's biosphere stumble through 5 mass extinctions, develop tool-using apes who immediately begin burning their own atmosphere and generally make a spectacular mess of things, you might reasonably decide to cut your losses, move on, try again with a cleaner setup. This is the failed experiment angle. Earth becomes a relic, a discarded draft, a version that simply didn't work out. The implications are philosophically brutal. It means we are not special, not chosen, not the centre of anyone's attention except our own. It means our entire existence, everything we've built, everything we've thought and created and destroyed, might be cosmically irrelevant noise to whoever sent 3i Atlas. The existential wound here cuts deeper than most threats. Asteroid impacts are terrifying but impersonal. The universe doesn't care about us. We've made peace with that. But being evaluated and rejected, being looked at, assessed and found wanting, that's different. That implies judgment. That implies we were given a chance and we failed. That somewhere in some cosmic filing system, there's a folder labelled Earth with a big red stamp discontinued. Now, to be fair, there's zero biochemical evidence for any of this. No genetic signature mismatch, no molecular fingerprint suggesting Earth life came from somewhere else. The evolutionary history we can trace going back billions of years is entirely consistent with purely terrestrial origins, chemistry in tidal pools, the RNA world hypothesis, gradual complexity building from simple replicators, standard abiogenesis. No alien intervention required. Scientists are understandably skeptical of external seeding hypotheses. Earth's biodiversity, its staggering complexity, its entire evolutionary tree, all of it makes perfect sense without invoking extraterrestrial sources. Occam's razor dictates go with the simpler explanation. Life arose here naturally, no help needed. The phylogenetic tree we've painstakingly constructed, tracing back through billions of years of evolution, shows continuous ancestry. Every organism on Earth shares common molecular machinery, the same genetic code, the same basic biochemistry, the same cellular structures. If Earth life came from elsewhere, if we were seeded, we would expect to see glaring discontinuities, inexplicable gaps, organisms with fundamentally different biochemistry appearing suddenly in the fossil record. We don't see that. But even so, even granting that Earth life is almost certainly homegrown, the possibility remains. The door stays open. Because if 3i Atlas truly is a seeder, if it really is heading for Europa, then the model becomes real. Someone is doing this. Someone possesses the technology and the will to spread life across star systems. And if they're doing it now, they could have done it before. Which raises the next terrifying question. If Europa gets seeded, if life takes root there, if it evolves, adapts, thrives in that alien ocean, what happens when it finds its way back? Part 5, the existential return path. Could seeded European life come here? Let's assume it works. Let's say 3i Atlas delivers its payload. Let's say the chemistry activates in Europa's ocean. Molecules replicate, complexity builds. Over millions of years, life takes hold. Not Earth life, something utterly else. Something adapted to crushing pressure, to total darkness, to chemosynthetic energy sources. Something that has never seen a sun. Could it come here? The question sounds absurd at first. Europa is unimaginably far away. Its ocean is sealed under miles of impenetrable ice. Nothing gets in, nothing gets out. But the solar system is not static. Objects move, impacts happen, and on timescales of millions of years, improbable events become inevitable. Mechanism 1, impact ejection. A massive asteroid or comet slams into Europa. The impact energy is enormous. Chunks of ice and water are blasted into space. Some of those chunks contain dormant microbe spores or frozen cells in suspended animation. They drift. They orbit for thousands or millions of years. Gravitational perturbations from Jupiter and the other planets subtly nudge some of these fragments into new, unpredictable trajectories. Eventually, statistically, some cross Earth's orbit. Some enter our atmosphere. Some survive re-entry and land. This isn't science fiction. It's proven science. We know Martian meteorites have reached Earth. We've found them. ALH8P4001, for instance. Rocks blasted off Mars by ancient impacts drifting through space for millions of years, landing in Antarctica. If it can happen with Mars, it can happen with Europa. The physics are well understood. Impact events on airless bodies or bodies with thin atmospheres can eject material at velocities exceeding escape speed. Mars's escape velocity is about 5 km/s. Some impacts deliver ejector at speeds twice that. Those rocks leave the Martian gravity well and enter heliocentric orbits. Then it's just a waiting game. Orbital mechanics over millions of years eventually bring some of those rocks to Earth. Europa's escape velocity is even lower than Mars, only about 2 km/s. That makes ejection far easier. An impact that might not eject material from Mars could eject substantial chunks from Europa. And Europa's environment, that subsurface ocean, means any ejector could potentially carry liquid water, flash frozen during ejection containing whatever organisms happen to be swimming nearby. Mechanism 2, Gravitational dynamics. Jupiter's gravity is monumentally powerful. It utterly dominates the outer solar system, but it also creates chaotic zones where orbital mechanics become terrifyingly complex. Debris trails, resonance effects. Over long enough timescales, material from the Jovian system can be flung inward. Not often, not predictably, but it does happen. Jupiter's hill sphere, the region where its gravity holds sway, extends millions of kilometers. Material within that sphere is perturbed by Jupiter's gravity, by the gravity of the Galilean moons, by solar tides, by passing objects. Most of that material remains trapped, but a fraction gets ejected, flung outward, or critically inward. And once it's free of Jupiter's gravitational dominance, it's at the mercy of broader solar system dynamics. Run orbital simulations. Start with 1 million particles scattered around Europa's orbit. Evolve the system forward 10 million years. Account for gravitational perturbations from all the planets, the Sun, even the larger asteroids. Some particles fall into Jupiter. Some escape the solar system entirely. But a small percentage, perhaps 0.1%, maybe even 0.01%, will eventually end up crossing Earth's orbit. Given enough time, delivery is inevitable. Mechanism 3. Engineered return. This one is far darker. If life on Europa doesn't just survive but evolves intelligence, or if intelligence was part of the payload from the beginning dormant and waiting, then intentional return becomes terrifyingly possible. Probe ships controlled descent to Earth. Not necessarily invasion. Perhaps curiosity, perhaps accidental contamination, perhaps something far more unsettling. This scenario demands Europa's ocean not just to support life, but to support the evolution of technological intelligence. That's a much higher bar. Intelligence is ecologically expensive. It requires immense energy. It requires ecological complexity. It requires selection pressure favouring bigger brains. On Earth, intelligence evolved in response to social competition tool use language. Would those same pressures exist in Europa's lightless crushing ocean? Maybe, maybe not. We simply don't know. But let's focus on the passive mechanisms, impact ejection and gravitational scattering, because those are inevitable given enough time. The question isn't whether material from Europa could reach Earth. The question is whether anything alive could survive the journey. Space is lethal. Vacuum radiation. Extreme temperatures, cosmic rays shredding DNA. Most organisms would die instantly, but extremophils exist. Tardigrades certain bacteria, organisms that can enter suspended states shut down metabolism and simply wait. If European life is adapted to Europa's environment already dealing with intense radiation from Jupiter's magnetosphere, already evolved for extreme conditions, it might just have a fighting chance. Tardigrades are the living proof of concept. These microscopic water bears can survive vacuum radiation temperatures near absolute zero desiccation. They enter a state called cryptobiosis. Metabolism stops. Biological time essentially stops. They are functionally dead by conventional definitions. But rehydrate them, warm them up, and they wake up resuming activity as if nothing happened. If European life evolved similar capabilities, if the environment selected for organisms that can tolerate extreme dormancy, because the ocean occasionally freezes or gets disrupted, then those organisms might indeed survive space transit. Frozen in ice, shielded from radiation by surrounding material dormant for millions of years. And when that chunk of ice lands on Earth, melts and releases its contents into a lake or ocean, they wake up. The timescale is crucial. This isn't a next decade threat. This is millions of years, perhaps tens of millions. The probability at any given moment is infinitesimal, but infinity is patient. And once the door is open, once life is established on Europa, the return path exists dormant waiting. Run a Monte Carlo simulation. Estimate impact frequency on Europa. Estimate ejection velocity distributions. Estimate survival rates for radiation exposure during transit. Estimate atmospheric entry survival. Estimate the probability of landing somewhere on Earth where the organism could take hold. Multiply all those probabilities together. The number you get is tiny, perhaps 10 out of 7, 15, maybe even smaller, but it's not zero. A non-zero probability is all you need for an existential risk. Because if even one viable organism makes it back, if it carries biochemistry incompatible with Earth's biosphere, if it's invasive, aggressive, chemically toxic to our cells, we're dealing with a contamination scenario we have no immune response for. No evolutionary history with. No natural predators or competitors calibrated to fight it. This isn't an asteroid strike. Asteroids are physics problems. You see them coming, you calculate trajectories you deflect or evacuate. This is biology, evolution, unpredictable, subtle, a slow invasion that might not even look like an invasion until it's far too late. Imagine the scenario. A meteorite lands in a Siberian lake, 2050, 2060, whenever. Nobody notices. It's small, no crater. It melts. Water seeps into the lake. 6 months later, fish start dying. Strange microbial blooms erupt. Water turns colours nobody has ever seen before. Scientists investigate find organisms with biochemistry that doesn't match anything in Earth's databases. They realise too late that it's spreading, adapting, competing with native microbes and winning. By the time we comprehend what's happening, it's in multiple water systems. Ocean currents carry it. Birds spread it. It's everywhere. And our ecosystems built on 4 billion years of Earth biochemistry simply cannot cope. Food chains collapse. Fisheries fail. Agriculture becomes impossible in contaminated regions. We're dealing with a biological invasion from a biosphere that never evolved. Alongside ours, never learned to coexist, operates by fundamentally different rules. Contrast this with conventional space threat narratives. Hollywood gives us alien armadas, Independence Day, War of the Worlds. Visible threats, obvious enemies. But real cosmic threats might look like nothing at all. A spore, a cell. A chemical signature in a water sample that nobody notices until entire ecosystems begin to collapse. The return path is remote, slow, speculative. But once Europa is seeded, once that ocean becomes a biosphere, the clock starts. And we're sitting here in the inner solar system, right in the eventual path of anything that gets ejected. The door is ajar, and we don't know what's on the other side. We don't know if it's friendly, hostile, or utterly indifferent. We don't know if it will even recognise us as life. We're just waiting, watching, hoping that if something does come back, we'll have enough warning to prepare. But preparation assumes understanding, and we don't understand. Not yet. Part 6, the Europa Ocean as an evolutionary accelerator. Close your eyes. Picture an ocean that has never ever seen light. 15 kilometres of ice above you. Pressure that would crush a submarine like a tin can. No photosynthesis, no sun-derived energy chains, just raw chemistry. Just heat seeping up from a rocky core endlessly tortured by Jupiter's immense gravity. Just darkness so absolute it becomes a physical presence. This is Europa's ocean, and it might be the perfect crucible to forge something entirely new. Icy moon oceans are critical because they offer what Earth doesn't: unparalleled stability over geological time. Earth's surface is a chaotic symphony of destruction. Continents drift. Climates swing wildly. Asteroid impacts are common. Supervolcanoes erupt. Ice ages come and go. Every few 100 million years, something catastrophic resets the evolutionary board. Life survives, but it starts over, it adapts, it pivots, but it never gets uninterrupted time to simply evolve. Europa doesn't have that problem. Its ocean has been there stable for billions of years. Conservative estimates suggest at least 3 billion, perhaps far longer. The colossal ice shell protects it from every conceivable surface catastrophe. No UV radiation penetrating to sterilize microbes. No solar wind stripping away atmospheres. No day-night cycles imposing a rhythm. Just stable, insulated, pressurized water with abundant energy flowing from below. An incubator, a controlled environment, a biological reactor that never ever shuts down. Energy is paramount. Life demands energy. On Earth, most ecosystems run on sunlight. Photosynthesis captures solar radiation, converts it to chemical bonds feeding everything else. plants algae, cyanobacteria. They form the base of the pyramid. But sunlight isn't the only option. Deep-sea hydrothermal vents are living proof. Black smokers on Earth's ocean floors host entire ecosystems based on chemosynthesis. Bacteria metabolizing hydrogen sulfide methane and other reduced compounds spewing from the crust. They don't need the sun. They build complex organic molecules from inorganic chemistry, utilizing geothermal energy. Europa has the exact same setup. Better, actually. Tidal heating from Jupiter's gravitational torque generates enormous heat in Europa's rocky mantle. Jupiter doesn't just pull on Europa, it squeezes it, flexes it, because Europa's orbit is slightly elliptical. That constant flexing generates friction. Friction generates heat. Billions of watts of thermal energy flow through the mantle into the ocean. That heat drives hydrothermal circulation. Water seeps down through cracks in the seafloor, gets heated to hundreds of degrees, dissolves minerals from the rock, and rises back into the ocean, carrying chemical energy. Gradients form redox pairs, electron donors and acceptors, everything you need to power chemosynthetic metabolism. Hydrogen, methane, sulfur compounds iron-dissolved gases, a veritable chemical buffet endlessly replenished. Now introduce the fast-track evolution hypothesis. In a stable, energy-rich environment with constant chemical gradients, providing selection pressure, evolution might accelerate. Not in terms of mutation rate, that's likely constant, but in terms of complexity accumulation. On Earth, evolution was constantly interrupted. Mass extinctions pruned the tree, reset the clock. Complexity had to painstakingly rebuild from whatever survived. Europa would not suffer that fate. No mass extinctions, no asteroid-driven die-offs, no climate catastrophes, just continuous, relentless pressure to adapt, optimize, compete. Mutations accumulate without catastrophic resets. Selection filters without wiping out entire lineages. Complexity builds incrementally generation after generation for billions of years. Over millions of years, simple chemosynthetic microbes could give way to exponentially more complex forms. Multicellularity, specialization, motility, cell differentiation, tissues, organs. On Earth, multicellularity evolved independently multiple times. It's a convergent solution to ecological problems. Bigger organisms can accomplish what smaller organisms cannot access. Different resources defend against predators, move through environments that would kill single cells. In Europa's ocean, those same relentless selection pressures might drive similar innovations. But without light, without photosynthesis, the evolutionary paths would radically diverge. No eyes, no visual systems, but perhaps electroreceptors for detecting faint bioelectric fields. Many organisms on Earth use electroreception: sharks, platypuses, electric fish. It works in water, it works in darkness. Maybe chemoreceptors sensitive to parts per billion concentrations of signaling molecules, tracking chemical plumes from hydrothermal vents, finding food, avoiding predators. Communication through complex chemical signals, pheromones. A dark ocean teeming with invisible conversations happening in dissolved molecules. Perhaps echolocation. Bats use it. Dolphins use it. Sound travels incredibly well in water, far better than in air. An organism capable of generating sounds and interpreting echoes could navigate, hunt, build sophisticated mental maps of its environment, all without ever seeing. And maybe structures we don't even have words for because we've never encountered them. Organs for detecting magnetic fields, pressure sensors that can read ocean currents with precision, biological accelerometers that track motion in 3 dimensions. Evolution is limitlessly creative. Give it enough time, enough energy and relentless selection pressure, and it will forge solutions we haven't even begun to imagine. Brain-like structures are not unique to surface life. They are solutions to information processing problems. And those problems exist anywhere organisms compete. If European life evolves predation, it will evolve nervous systems. Predators need to track prey. Prey needs to evade predators. That's an arms race. Neural complexity increases on both sides. Eventually you get brains, perhaps small, perhaps distributed, perhaps fundamentally different from vertebrate brains, but functional, capable of learning memory decision-making. This is dark ecological bootstrapping. Life starting in total darkness and building complexity without any reference to Earth's playbook. No photosynthesis means no oxygen from photosynthesis. Europa's ocean is almost certainly anoxic. Low oxygen, maybe no oxygen at all. That changes everything. Earth's evolution got supercharged when oxygen appeared, allowing for highly efficient aerobic metabolism, which produces vast amounts of energy, enabling large complex organisms. But anaerobic metabolism works too. It's less efficient, producing less energy per glucose molecule, but it works. Earth had anaerobic ecosystems for billions of years before oxygen appeared. Fermentation, methanogenesis, sulfate reduction. Complex ecosystems running on chemistry that doesn't need oxygen. European life might never develop oxygen-based metabolism. It might never need it might build complexity through sheer time and stable conditions, compensating for lower energy efficiency with billions of years of uninterrupted evolution. The timeline is the key. Alien bioengineers, if they exist, might operate on million-year cycles. For them, seeding Europa isn't a quarterly project. It's a legacy, a long-term investment. They launch the payload and wait. Maybe they check back in a million years, 10 million. Maybe they don't. Maybe they've seeded 1,000 worlds and only expect 10 to succeed. But success on even one justifies the immense effort. Possible divergence. European life, even if seeded from the same source as Earth life, would evolve in radically different directions. Different selection pressures, different environmental constraints, different available niches. Over millions of years, biochemistry could drift. The morphology could become utterly unrecognizable. You might end up with something that shares a common ancestor with Earth life, biochemically speaking, but looks and functions nothing like it. Different proteins, different metabolic pathways, different cellular structures, all exquisitely optimized for high pressure, low temperature, and total darkness. This could be the greatest evolutionary experiment ever conducted. A blank slate ocean, controlled conditions, seeded chemistry. Just add time and watch what emerges. For the seeders, it's a gamble. For us, it's a threat we cannot yet quantify. But what about the humans managing our own space exploration? What do the institutions tasked with planetary protection truly think about all this? Part 7. The hidden battle in planetary protection agencies. Planetary protection sounds mundane. It conjures images of endless paperwork, bureaucratic committees and dry guidelines, the kind of machinery that makes your eyes glaze over. But right now, behind tightly closed doors, the people who run these systems are having profoundly uncomfortable conversations. COSPAR, the Committee on Space Research. NASA's Office of Planetary Protection, the European Space Agency's equivalent divisions, these are the gatekeepers. These are the individuals who decide what level of sterilization your spacecraft requires before you send it to Mars or Europa or anywhere else we suspect might harbour life. They've developed a rigid classification system, categories 1 through 5, each with specific escalating protocols for contamination prevention. Category 1 is Easy the Moon, Mercury bodies where life is impossible, no protection needed. Category 2, mostly harmless targets with slightly elevated standards. Category 3, flyby or orbital missions to bodies of biological interest. Category 4, landers and rovers to those same bodies, much stricter, demanding rigorous sterilization, heat treatment, chemical cleaning, and meticulous documentation of every single component. Category 5 is the terrifying one. That's for sample return missions bringing material back from potentially habitable bodies. The protocols are draconian absolute containment sterilization, on return indefinite quarantine because the risk runs both ways. Forward contamination, we send Earth microbes to another world and accidentally seed it with our own biology, irrevocably altering its pristine state. Backward contamination, we bring something back that doesn't play nice with Earth's biosphere, potentially unleashing an unimaginable biological catastrophe. Apollo missions faced this. Astronauts returning from the moon were immediately placed in quarantine, not because anyone seriously believed the moon hosted life, but because we didn't know for certain. Better safe than sorry. The quarantine facility was extensive 3 weeks of isolation, constant medical monitoring, exhaustive testing. Only after we had brought back enough lunar samples to be scientifically confident there was nothing alive did we relax those protocols. But 3i Atlas utterly shatters this model. It's not a spacecraft we built. It's not a mission we can control. It's an uncontrolled variable, a cosmic wildcard entering our system from outside. If it carries exotic organics, if it delivers biological material to Europa, it violates every single assumption underpinning existing planetary protection frameworks. Because those frameworks were meticulously designed for human missions, for controlled scenarios, for situations where we are the actors. This is different. This is passive receipt of potentially biotic material from an external source. There is no category for that, no protocol, no established response. Do we attempt to intercept it? Do we try to sterilize it somehow out in the blackness of space? Or do we simply observe and document hoping for the best? Nobody has written the rulebook because nobody ever expected this scenario to materialize. Rumour has it, and this is strictly unconfirmed, that some scientists and officials are profoundly worried. Not publicly, not in press releases, but in internal memos in hushed closed-door sessions at conferences. The concern centres on cross-contamination in both directions. If 3i Atlas seeds Europa, that is forward contamination from an unknown source. We lose the ability to study Europa as a pristine environment. Any life we find there will never know if it was native or deliberately delivered. The immeasurable scientific value of Europa as a natural laboratory gets irrevocably compromised. But worse, far worse, if seeded European life eventually makes its way back to Earth through impact ejection or other mechanisms that's backward contamination from a biosphere we did not create and do not understand. Our planetary protection protocols assume we control the contamination source. We sterilize our spacecraft. We choose when and where to take samples. We can enforce quarantine, but with natural transfer we have no control. Material arrives uninvited. No warning, no containment. Imagine the crisis scenario. A probe returns from Europa, maybe in 2040, maybe 2050. Some future mission designed to collect subsurface ocean samples and bring them home for analysis. Perhaps the containment system works perfectly. Samples remain sealed. Everything gets studied in biosafety level 4 labs under maximum containment. But what if there's a microscopic leak? What if one tiny seal fails? What if an organism smaller than our filters slips through? Or worse, imagine the natural transfer scenario, a European meteorite blasted off the moon by an impact drifting through space for 1 million years, finally landing in Siberia or Antarctica or the vast unmonitored ocean. It melts, releases its contents. Nobody knows it happened because nobody was watching for it. By the time we detect anomalous microbial activity, it's already spread. Agencies might face an impossible choice: strict containment or even moratoria. Halt all missions to potentially seeded worlds. Treat the entire Jovian system as a contamination zone. Establish exclusion perimeters, no-fly zones. But that's politically and scientifically untenable. We want to explore. We need to explore. The public expects it. Funding depends on it. Congress or Parliament won't approve budgets for space exploration if we're telling them we can't actually go anywhere interesting. So the tension builds. Urgency versus inertia. Institutional caution versus insatiable scientific curiosity. The scientists desperately want samples, want data, want to know if there's life in Europa's ocean. But the planetary protection officers are absolutely terrified of bringing something back that could devastate Earth's biosphere. Ethical questions pile up like a cosmic avalanche. Do we have the right to interfere with a seeding event, assuming 3i Atlas is one? If alien bioengineers spent millions of years planning this, if they calculated trajectories and packed payloads, and launch 3i Atlas with specific goals, do we have the authority to sabotage that? To sterilise their work, to prevent their experiment from proceeding? These aren't just strategic questions, they're profoundly ethical ones, philosophical ones, and nobody's asking them publicly because officially 3i Atlas is just a comet. Nothing to worry about. Move along. But here's the darker thought. Maybe agencies suppress concerns not out of malice, but out of grim pragmatism. Public panic serves no one. If you announce that an interstellar object might be seeding alien life in our solar system, and that life could eventually contaminate Earth, what happens? Stock markets crash. Religious institutions fracture. Conspiracy theories metastasize. Social media explodes with unchecked fear. Politicians demand action. Activists demand inaction. Everyone suddenly claims to be an expert. Everyone has an opinion. Better perhaps to stay quiet, monitor, prepare behind the scenes, hope nothing goes wrong. If it does go wrong, if contamination happens, deal with it then. Crisis management rather than crisis prevention. It's cynical, but it's also chillingly realistic. Institutions are built to manage risk, not to terrify populations. That tension between transparency and stability is a narrative goldmine because the public deserves to know. Democratic societies function on informed consent. If there's a potential existential threat, citizens should be told, should have input on how to respond. But institutions know that public panic can be more dangerous than the threat itself. Misinformation spreads faster than facts. Fear drives irrational decisions. Sometimes secrecy does protect. Where is that line? When does a legitimate need to know become unethical concealment? These aren't easy questions, and 3i Atlas forces them into the open whether anyone is ready or not. Planetary protection frameworks are evolving. They have to, because 3i Atlas isn't the first interstellar object, and it absolutely won't be the last. Which raises the next crucial question: has this happened before? Part 8. Alternative seeder candidates. Has this happened before? Before 3i Atlas, we had 2 confirmed interstellar visitors, Oumuamua in 2017 and 2i Borisov in 2019. Both had hyperbolic trajectories, both originated from outside our solar system, and both were strange in their own unique ways. Oumuamua was the truly bizarre one, elongated, tumbling, reflecting light in ways that didn't match typical comets or asteroids. Most unsettlingly, it accelerated slightly without visible outgassing. That acceleration was tiny, measured in millimeters per second squared, but it was real, precisely measured and confirmed across multiple observations. Scientists proposed various explanations, outgassing too faint to detect visually, but still producing thrust. Radiation pressure on an unusually flat, reflective surface acting like a light sail. Hydrogen ice sublimating invisibly because hydrogen doesn't show up in typical spectroscopic observations. Each explanation had its problems, none fit the data perfectly. Some people, not mainstream scientists, but certainly not complete cranks either, suggested it might be artificial, a probe, a light sail, something deliberately built. This hypothesis garnered significant attention because Avi Loeb from Harvard, a respected astrophysicist, publicly backed it. Not conclusively, but enough to argue we shouldn't rule it out without more data. That caused immense controversy. Mainstream astrophysicists pushed back extraordinary claims require extraordinary evidence. Oumuamua's behaviour, while odd, wasn't that odd. Natural explanations remained statistically more probable. But the debate exposed something crucial. Our detection methods are inherently biased. We look for what we expect: comets with comey asteroids with rocky surfaces. Anything that doesn't fit those rigid templates gets classified as weird. But we simply don't have established frameworks for recognising unequivocally artificial objects. If someone sent a probe through our solar system, would we even know? Could we truly tell the difference between a bizarre natural object and a deliberately engineered one? Perhaps not. 2i Borisov was more conventional. It looked like a comet. It behaved like a comet. It had an outgassing coma and a tail. Its chemical composition was broadly similar to solar system comets, but with subtle variations suggesting a different formation environment. Unremarkable except for its undeniable interstellar origin. Confirmation that interstellar comets do exist and occasionally wander through, but that's the key word, occasionally. 3 objects detected in 8 years. Oumuamua in 2017, 2I Borisov in 2019, 3I Atlas in 2025. That's a detection rate of roughly 1 every 2.3 years. Sounds rare, but is it sky surveys before 2010 were far less sensitive. Telescopes weren't optimized for detecting fast-moving faint objects on hyperbolic orbits. Pan-STARRS, the survey that found Oumuamua, only came fully online in 2010. Before that, we had less coverage, less sensitivity, slower response times. An interstellar object passing through might have gone completely unnoticed. Estimates suggest we miss most of them. Perhaps 10 for every one we detect, maybe even 100. The solar system is vast. The sky is immense. Even with modern surveys, we're only sampling a fraction of the total space. Statistically, interstellar visitors might be common passing through all the time. We just don't see them. If that's true, if interstellar objects cross the solar system regularly, then 3I Atlas isn't anomalous. It's expected. And if some fraction of those objects are seed ships if directed, Panspermia is a common practice among advanced civilizations, then we are swimming in biology we simply don't recognise. Speculative simulation studies suggest exactly that. Astrophysical models show that small interstellar debris, comets' icy bodies ejected from planetary systems during formation, should cross stellar neighbourhoods regularly, especially early in galactic history when stellar densities were higher and gravitational scattering more frequent. Our solar system could have been pelted with interstellar objects throughout its entire history, billions of them. Most passing through, some impacting, some delivering material. Now consider certain geological and paleobiological mysteries, the Cambrian explosion. Approximately 540 million years ago, life on Earth suddenly diversified with astonishing speed. Complexity exploded. Hard-bodied organisms appeared in the fossil record seemingly overnight, geologically speaking over maybe 10 million years, which is a mere blink of an eye. Mainstream science explains this through a confluence of environmental changes, rising oxygen levels, intensified predator-prey dynamics, creating evolutionary arms races, Hox genes enabling new body plans, ecological feedback loops. It makes scientific sense. The evidence fits. But the timeline bothers some people. Why then? Why not earlier? Life existed for billions of years before the Cambrian. Why did complexity wait? Fringe hypotheses ask, what if there was an external trigger? What if interstellar material delivered genetic information or chemical catalysts that rapidly accelerated evolution? Not seeding life from scratch. Earth already had life, but introducing new biochemical tools, new genetic sequences, new evolutionary possibilities. Most scientists dismiss this. Earth's evolutionary history makes sense without invoking external sources. The Cambrian explosion is explainable through natural processes. Genetic studies show that the body plans appearing in the Cambrian were built from genes that already existed. No foreign DNA, no alien insertions, just existing genes repurposed in novel ways. But the hypothesis persists. It persists because we can't rule it out with absolute certainty. Genetic evidence from 540 million years ago is sparse degraded. We're reconstructing history from fragments. If interstellar material did deliver something, if it integrated into Earth's biosphere subtly, we might not detect it now. The signature could be diluted, overwritten by billions of years of subsequent evolution. If that's true, if Earth's biosphere was seeded or reseeded multiple times over eons, then life here is a palimpsest, layers written over layers. Each interstellar delivery event adding new chemistry, new information, new possibilities. 3I Atlas wouldn't be unique, it would be the latest in a long series. One more delivery in a process that's been ongoing for billions of years. But direct evidence is sparse. Cosmic dust erodes. Geological recycling churns the crust. plate tectonics subduct seafloor, volcanism resurfaces continents, interstellar origin signatures get diluted over billions of years. Even if seeding events happened, even if meteorites carrying alien biochemistry landed regularly, proving it would require finding molecular fingerprints that survived intact. And those fingerprints, if they exist, are buried under eons of terrestrial chemistry. Alternative hypothesis may be interstellar comets simply sample a broader chemical diversity than solar system comets. What looks strange to us, that high carbon dioxide ratio in 3I Atlas, those organic crusts, might be perfectly normal elsewhere. Our baseline is biased. We've only studied comets born in our solar system, formed from the same protoplanetary disk with the same starting chemistry. Interstellar comets come from utterly different stellar environments, different metallicity, different radiation fields, different formation temperatures. Of course they look different. This reframes 3I Atlas not as a unique freak, but as part of a hidden interstellar ecosystem. Objects drifting between stars, carrying chemistry from one system to another, occasionally interacting with planets and moons. A cosmic web of material exchange happening constantly and visibly over galactic timescales. If that's the case, then 3I Atlas is just one thread in a much larger tapestry, and Earth sitting here in the Milky Way suburbs has been part of that tapestry all along. We just didn't notice because we weren't looking. We assumed we were isolated, special, unique. But maybe we're just one node in a vast network that spans the galaxy, receiving packages we didn't order, sending packages we don't know about through impact ejection, part of a system we barely understand. But what if it's not passive? What if the 3I Atlas isn't just drifting? What if it's being steered? Part 9. The Megastructure. Whisper are Atlas's jets' guidance systems. Comets outgas. That's their defining behaviour. As they approach the sun, solar radiation heats their surface. Ice sublimates. Gas and dust jet into space. This process is typically random, chaotic, driven by surface features, cracks pockets of volatile ice rotating in and out of sunlight. There's no pattern, no rhythm, just irregular bursts as different parts of the nucleus heat up and cool down. Except 3I Atlas might have a rhythm. Reports from media outlets citing speculations from fringe but mathematically literate theorists describe a heartbeat brightness, approximately 16 hours, repeating consistently over multiple observation periods. Not the irregular flickering you'd expect from random outgassing, but something more structured, more periodic, like a clock ticking in the void. Why is that strange? Because comets don't usually do that. Rotation causes brightness variation, sure as different surfaces reflect light. If a comet has an elongated shape, you see brightness peaks when the long axis points toward you, dips when it rotates edge on. But that's typically gentle sinusoidal. 3I Atlas shows sharper variations. Peaks at regular intervals, like something turning on and off. Periodic jetting, outgassing events that recur with clock-like regularity. That is uncommon. Suspicious. It suggests either an incredibly unusual surface structure with volatiles distributed in perfect, almost impossible symmetry, or something else, something controlled. One model suggests low-thrust navigation. In spacecraft engineering, you can nudge an object's orbit using gentle, sustained thrust. Ion propulsion gas jets. Small forces applied over long durations. You don't need massive engines, just immense patience and precision. Change velocity by meters per second over months or years. Adjust trajectory by fractions of a degree. Over interstellar distances, those tiny adjustments add up significantly. If 3I Atlas's jets aren't random, if they're positioned symmetrically and firing periodically, they could function as a subtle navigation system. Tiny course corrections, meticulously adjusting its trajectory toward a specific target Europa, or perhaps Ganymede, which also has a subsurface ocean, or Enceladus at Saturn, another prime candidate, or some other icy moon we're not even thinking about yet. The thrust wouldn't need to be large. Comet nucleus masses are relatively small, a few billion kilograms. A jet producing even a few newtons of thrust sustained over months could change velocity significantly, and if those jets fire periodically precisely timed to rotation, you gain directional control. Fire when a specific surface faces the desired thrust direction over and over. Rotation becomes your gimbal. Some fringe communities point to what they call tri-point symmetry, multiple jets appearing at roughly 120-degree intervals around the nucleus revisited over several rotation periods as if someone placed them there, as if they are precisely engineered nozzles, not random cracks. Engineered features designed to produce thrust in specific controlled directions. But let's pump the brakes. Natural explanations exist and they are powerful. Mainstream astrophysicists argue the jets are exactly what they look like: dust and gas outbursts from solar heating. Observations confirm that 3I Atlas looks and behaves like a comet. The European Space Agency and other institutions have stated this explicitly. It has a coma. It has a tail formed by solar wind and radiation pressure. It follows predictable outgassing patterns as it approaches and recedes from the sun. The periodic brightness variations could be explained by an irregular shape, combined with a very specific, non-uniform, volatile distribution. If one side of the nucleus has more carbon dioxide ice, it outgasses more strongly when that side faces the sun. Rotation brings that side around every 16.16 hours. Brightness peaks, simple. No need to invoke guidance systems. So why the persistent speculation? Because the same data can support multiple interpretations. If you're predisposed to think 3I Atlas is natural, the jets look natural. If you're predisposed to think it might be engineered, the jets look artificial. Confirmation bias runs both ways. We see what we expect to see or what we want to see. Here's the core tension: we don't have close-up imagery. No spacecraft has approached the 3I Atlas. Everything we know comes from telescopes millions of kilometers away. We're watching pixels, interpreting light curves, fitting models to sparse data, making educated guesses based on incomplete information. And in that ambiguity, speculation thrives. What would it take to know for sure? A flyby mission. A probe equipped with high-resolution cameras, spectrometers, mass sensors. Get within a few hundred kilometers, image the nucleus directly, map its surface, identify the precise jet sources, measure its chemical composition in situ, determine if those jets are coming from random cracks or specific engineered nozzles. But we don't have that. We won't have that. 3I Atlas is moving too fast. By the time we could launch an intercept mission, it would be gone. Past Jupiter, heading rapidly out of the solar system, lost forever to the darkness. Our window for detailed observation is narrow, and it is closing fast. We get what we get from Earth-based telescopes, and that's it. Ask yourself, what if we're witnessing the first known interstellar probe cunningly disguised as a Comet A, cosmic Trojan horse designed to look utterly unremarkable to pass through solar system defences, if any exist, without triggering alarms to deliver its payload quietly, while everyone assumes it's just another icy rock from the void? That's the narrative hook. The chilling possibility, however remote, that we're being played. That 3I Atlas is far smarter than it looks. That someone somewhere launched this object knowing we'd classify it as natural, knowing we'd dismiss speculation as conspiracy theory, knowing we'd do exactly what we're doing, watch it, catalogue it, and then move on. But even if the jets are natural, even if every skeptical scientist is right, and this is just a weird comet with unusual chemistry, the fact remains: 3I Atlas is heading toward Jupiter, and whether it's guided or drifting, engineered or natural, the outcome might be precisely the same: payload delivery to Europa, a seeding event, a new biosphere. Which brings us to the ultimate conspiracy layer. Because if 3I Atlas really is significant, if it really could deliver alien biology to Europa, would governments tell us, or would they act in secret? Part 10, the conspiracy layer. Black site missions toward 3I Atlas. Picture a classified launch. Middle of the night, a remote facility somewhere in Kazakhstan or French Guiana. No press, no public announcement, no satellite trackers notified. A rocket lifts off carrying a small, impossibly fast probe, designed for one singular purpose: to intercept an interstellar object before it reaches the Jovian system. Analyze it, sample it, maybe even redirect it. And never tell anyone. This is rumour territory. Unconfirmed, highly speculative, the kind of thing discussed on fringe forums in encrypted chat rooms by people who claim insider knowledge but offer no verifiable proof. Yet the forums are buzzing. Communities tracking orbital elements launch windows. Telemetry gaps claim that 2 major spacefaring nations clandestinely launched probes aimed at 3i Atlas. High-velocity trajectories, nuclear or solar electric propulsion, minimal radar cross-section. Launched under deep cover stories, deep space tests, experimental navigation, classified defense projects. Why might such secrecy exist? The stakes are geopolitical and scientific. Accessing an interstellar object, especially one suspected of carrying biological material, could provide an unprecedented strategic advantage. Early detection of alien technology or biology. First mover control of a potential payload. Unimaginable scientific bragging rights in a new unspoken space race. Or perhaps precautionary containment. If 3i Atlas truly is a threat, it would be far better to intercept it far from Earth, far from populated moons before it delivers anything. Sterilize it, vaporize it, redirect it irrevocably out of the solar system. Problem solved silently. Hypothesized probe profiles include small spacecraft, perhaps a few hundred kilograms with high delta-V capability, meaning massive velocity changes are possible. Chemical propulsion for the initial boost, then ion drives, or nuclear electric propulsion for sustained acceleration. Minimal public emissions, no easily observable exhaust plume. Launch during optimal windows when Earth's orbit aligned with intercept opportunities. Trajectory designed to match 3i Atlas's hyperbolic path rendezvous. At specific coordinates, conduct a flyby, or sample collection, then escape or impact depending on mission goals. Orbital evidence, or what proponents claim is evidence, includes micro-perturbations in 3i Atlas's trajectory. Tiny deviations from a pure gravitational path measured in meters per second, too small to be natural gravitational interactions, too consistent to be mere measurement error. Offered as indirect evidence of momentum, transfer from probe interactions, close flybys that exchange momentum, maybe even physical contact samples, scoops, harpoons, dust collectors, but no peer-reviewed data confirms this, no official telemetry, no press releases from space agencies, just spreadsheets on forums, graphs with unlabeled axes, claims without sources, kind of evidence that convinces people who want to be convinced and persuades nobody else. The intelligence community's motivation makes terrifying sense if you squint. Control of extraterrestrial biology could irrevocably reshape geopolitics. Imagine being the first nation to decode alien biochemistry, to understand how life can be engineered and delivered across star systems, to reverse engineer biological technologies we don't possess, to develop new materials, new medicines, new agricultural methods based on alien cellular machinery. That's leverage. That's power. That's the kind of advantage nations build militaries to protect. Even if 3i Atlas carries nothing biological, even if it's just unusual chemistry, getting samples first means scientific dominance, publications, patents, Nobel Prizes, institutional prestige. Universities and research institutes compete viciously for discoveries. Nations even more so. Being second is being forgotten. Or maybe the motivation is purely defensive. If 3i Atlas really is seeding Europa, if that creates the potential for backward contamination to Earth, then intercepting it becomes a matter of planetary defense, not against kinetic impact but against biological invasion. Sterilize the payload before it reaches Europa. Prevent contamination. Protect Earth's biosphere from unknown alien biochemistry. That's a legitimate national security concern. So why do mainstream scientists discount these rumours entirely? No formal mission announcements. NASA's public schedule shows nothing. ESA's launch manifest has no mysterious gaps. Roscosmos, CNSA, same story. Budget allocations are public for most democratic space programs. Black budgets exist, but they're typically for military satellites, not interstellar probes. And the 3i Atlas is too far too fast. Intercept missions require years of planning. You cannot launch on short notice. No infrared signatures from high-velocity launches detected by monitoring satellites. Every rocket launch produces heat, vast quantities of it. Infrared detection satellites operated by multiple nations for missile early warning would undeniably see a launch, even from remote sites, even classified ones. No anomalous launches reported during windows that would enable a 3i Atlas intercept. And agencies like NASA and ESA have stated repeatedly that 3i Atlas is a natural comet, nothing more. Observations match comet behaviour. Chemistry fits expectations for interstellar objects. No evidence of artificial structures, no anomalous signals, just a comet doing comet things. So why do the conspiracy theories persist with such tenacity? Because secrecy breeds suspicion. Because governments have lied about space programs before. U-2 flights, Corona spy satellites, space shuttle military missions, all classified, all denied publicly until decades later, when declassification revealed the truth. People remember, people extrapolate, and because the stakes if 3i Atlas is what some people think it is, are high enough to justify black site operations, if alien biology exists, if it's accessible, if controlling it provides an insurmountable advantage, then of course nations would pursue it secretly. Denials mean nothing. Lack of public evidence means nothing. Absence of evidence isn't evidence of absence. The psychology of secrecy matters here. Humans fear the unknown. We construct narratives to make sense of ambiguity. When institutions won't give us answers, when data remains classified or unavailable, we fill the gaps with speculation. Sometimes that speculation is wrong, paranoid and unfounded. Sometimes it's chillingly closer to the truth than official statements. History provides examples of both outcomes. A morality play is humanity ready to intercept a potential seed ship. Do we even have the right to interfere with a cosmic-scale biological experiment? If alien bioengineers spent millions of years planning this, if they calculated trajectories and packed payloads, and launched 3i Atlas with specific goals, do we have the authority to sabotage that, to sterilize their work, to prevent their experiment from proceeding? These aren't just strategic questions, they're profound ethical ones, philosophical ones, and nobody's asking them publicly because officially 3i Atlas is just a comet. Nothing to worry about. Move along. But the cosmos doesn't stop with 3i Atlas. Zoom out. Look at the broader picture. Other phenomena, other anomalies, other hints that the universe is stranger, far stranger than we are ready to accept. Part 11, December 2025. Gravitational wave mystery, the Rogue Spike event. Gravitational wave detectors hum in the darkness. LIGO in Louisiana and Washington. State Virgo in Italy. Kagra in Japan. Massive instruments, kilometre-long laser interferometers, listening for ripples in space-time caused by colliding black holes, merging neutron stars, other catastrophic cosmic events. Most signals fit known patterns, binary and spirals, spiraling inward frequency, increasing amplitude, growing then merger and ring down. Predictable waveforms precisely matching general relativity's predictions. But recently in December 2025, a signal appeared that didn't match anything in the catalogue. Dubbed the Rogue Spike event, it was brief, intensely powerful, lasting perhaps half a second. Its shape was wrong. Its frequency evolution didn't follow standard in spiral patterns. Its amplitude spiked suddenly without the gradual build-up you expect from orbital decay. It just appeared peaked and vanished. Standard explanations were immediately floated: an instrumental glitch, a seismic event near one of the detectors creating noise that mimics gravitational waves, a cosmic ray hitting sensitive optics, a lightning strike, an earthquake, a calibration error. These detectors are exquisitely sensitive to everything: trucks driving past, ocean waves, earthquakes on the other side of the planet. Teams spent months meticulously ruling out terrestrial noise, before confirming astrophysical sources. The rogue spike underwent preliminary analysis, no obvious terrestrial source identified. It appeared in multiple detectors with appropriate time delays for signal propagation, immediately ruling out local glitches. If it was noise, it would appear at random times in each detector. Correlated signals strongly suggest real gravitational waves, but the waveform simply doesn't fit established models. Not a black hole merger. Those produce characteristic chirps, not a neutron star merger. Those have different frequency evolution, and often produce electromagnetic counterparts we can detect with telescopes. None found. Not a supernova core collapse. Those produce longer duration signals with different characteristics. Nothing matches. So what else? Exotic possibilities emerged. A disruptive dark matter clump. If dark matter can clump densely enough, gravitationally interact strongly enough, perhaps it produces detectable space-time distortions. Pure speculation with no prior evidence that dark matter clumps like that. But gravitational wave astronomy is a nascent field. We've only been listening for a decade. Perhaps there are sources we haven't even imagined. An exotic compact object, something between a black hole and a neutron star, a quark star, a strange star, a graver star. Objects predicted by some theoretical models but never confirmed. Perhaps one existed. Perhaps it underwent some catastrophic, utterly unknown event. Maybe that's what we detected. Or if you're willing to entertain truly speculative hypotheses, advanced propulsion. Space-time distortions caused by technology we cannot yet imagine. If a civilization has mastered gravity manipulation, if they can warp space-time for faster-than-light travel, or other purposes that would undeniably produce gravitational waves. Maybe the rogue spike was a ship activating its drive. Maybe someone just jumped a warp nearby within astronomical observation range. Astronomically speaking, connect this to 3i Atlas. If there are unknown cosmic objects or technologies generating gravitational effects we don't understand, maybe 3i Atlas is just one of many unknowns. Part of a broader class of interstellar actors operating with physics we haven't even begun to decode. Objects that look natural but aren't. Technologies cunningly disguised as natural phenomena. A hidden layer of cosmic activity we're only just beginning to detect. The larger question is, daunting how much of the cosmos is utterly invisible to us, because our detection tools are tuned only for expected phenomena. We build gravitational wave detectors to find black holes and neutron stars because we know they exist. General relativity precisely predicts their signals. We know exactly what to look for. But what about things we haven't predicted? Things that don't fit our models, signals outside our search templates. We might be swimming in gravitational wave sources we simply cannot recognize. Glitches we discard as noise might be real signals from profound unknown sources. The cosmos might be far noisier than we think, but we're filtering aggressively, keeping only signals that match our existing templates, discarding everything else. What if we are throwing away the most interesting data? Implications for directed panspermia. Perhaps advanced civilizations utilize physics we're only beginning to glimpse. Propulsion mechanisms that create unique gravitational signatures, exotic matter configurations, quantum-engineered objects that manipulate space-time at will. If 3i Atlas is engineered, it might leverage principles we would currently classify as impossible: negative mass Alcubierre drives, traversable wormholes, technologies that look like magic because we don't understand the underlying physics. Narrative hook. The cosmos may be noisier, stranger, more active than textbooks admit. 3i Atlas might be one whisper in a symphony we're only starting to hear. The rogue spike might be another. We are detecting the faint edges of something far larger, a hidden architecture, a cosmic infrastructure built by intelligences that operate on scales we cannot yet comprehend. And we're just beginning to develop instruments sensitive enough to even notice. But maybe the weirdness isn't just astrophysical. Maybe it goes deeper. Maybe quantum mechanics, the very foundation of reality itself, is trying to tell us something critical. Part 12. The quantum mirror experiment that shouldn't have worked. Quantum mechanics is supposed to be fragile. Quantum states decohere. Entanglement breaks down over distance and time. Information gets irretrievably lost to environmental noise. That's the conventional wisdom. That's why quantum computers require extreme isolation, millikelvin temperatures, near-perfect vacuum magnetic shielding, vibration, isolation. Because the quantum world is exquisitely delicate. Interact with the environment even slightly, and coherence collapses. Quantum information becomes classical noise. Except recently a 2025 experiment demonstrated something utterly strange: quantum coherence, and what the researchers called state reflection, across far greater distances than anyone expected. Not meters, not kilometers. Scales that violate everything we thought were hard limits. The paper is still in peer review. Results haven't been independently replicated yet. But if confirmed, it challenges foundational assumptions about quantum mechanics itself. The experiment involved entangled particles. A standard setup: generate pairs using parametric down conversion, separate them, place them in different locations, and attempt to maintain coherence. Usually coherence lasts microseconds, maybe milliseconds under perfect laboratory conditions. But this experiment reported coherence persisting for seconds, even minutes, in some trials over distances of hundreds of meters, through environments that should destroy entanglement instantly. Somehow the states persisted. Somehow the information remained intact. The researchers don't fully understand why. They controlled for everything, eliminated known decoherence mechanisms, shielded against electromagnetic interference, isolated from vibration. But coherence lasted far, far longer than theory predicts. One leading hypothesis: there's a protective mechanism we don't understand. Some inherent property of the quantum states themselves that actively resists decoherence. Perhaps certain entangled configurations are more robust than others. Perhaps information can be encoded in ways that inherently survive environmental interaction, a form of quantum error correction, but naturally occurring rather than painstakingly engineered. Why does this matter for panspermia? Because if quantum states can preserve information over unexpectedly long distances and timescales, then perhaps advanced civilizations encode life or instructions for life at quantum or subatomic levels. Embed them within interstellar objects, transmit them remotely, bypassing the brutally unforgiving classical constraints of interstellar travel. Deep biology, bulky DNA molecules, complex proteins, fragile cell membranes, all are incredibly vulnerable to radiation. Cosmic rays shred DNA. UV radiation breaks chemical bonds. Over interstellar journeys lasting millions of years, classical biological material inevitably degrades. Even with protection, even frozen damage relentlessly accumulates. Eventually you're left with molecular wreckage, nothing viable. But what if the real payload isn't biological mass? What if it's information, quantum-encoded patterns stored in the material's subatomic structure? Information that doesn't degrade because it's protected by quantum coherence. The Comet delivers the hardware, the atoms, the molecules, but the software, the instructions, exist at a quantum level we can't yet measure. When 3I Atlas reaches Europa, when it impacts or fragments, when its material enters the ocean and encounters liquid water, the quantum information activates, interacts with local chemistry guides, molecular assembly, and bootstraps into macroscopic structures. Chemistry replicates according to quantum blueprints. Life begins. A bridge to 3I Atlas, more concretely maybe what we're seeing as cometary material, is just a carrier, a shell. Protective packaging. The true payload is encoded in quantum structures within that material. Chemical memory that activates under certain stimuli, specific temperatures, pressure thresholds, radiation exposure, contact with liquid water. Each triggers a different quantum information release. Europa's ocean provides the environment. The quantum information provides the recipe. You don't need to send living cells. Just send the instructions for building them. Let local atoms do the work. Self-assembly driven by quantum templates. It's efficient, robust, elegant. The implications are enormous. Seeding becomes drastically cheaper, far more efficient. No need to keep organisms alive during transit. No need for complex life support. Just send information and let local chemistry execute the program. This dramatically reduces payload, mass reduces energy requirements, and makes panspermia scalable across galactic distances feasible, even for civilizations that don't have unlimited resources. The philosophical edge is razor sharp. If life can be downloaded, what does that make us? Are we hardware running someone else's software? Are we the output of a program we didn't write? And if a civilization can encode life quantum mechanically, what else can they encode? Consciousness, intelligence, purpose, memories. Are we executing instructions from beings who existed millions of years ago in another star system? These questions offer no comfortable answers. They imply we lack free will, that our evolutionary history is predetermined guided, that everything we think we've discovered we were meant to discover, every technology we've developed we were programmed to develop. We're not authors of our own story, we are characters in someone else's narrative. Caution and skepticism are paramount. Current quantum experiments do not show biologically meaningful data transfer. Coherence persisting longer than expected is profoundly interesting, but it's a colossal leap from maintaining coherence to encoding complex information to transmitting life instructions across star systems. Applying quantum coherence to panspermia is highly speculative, far beyond mainstream science. Most physicists and biologists would call it unfounded extrapolation. But even as theory, even as a thought experiment, it expands our imagination, forces us to consider alternative mechanisms for life delivery, and makes us question fundamental assumptions about what's possible. And in science, questioning assumptions is precisely how progress happens. Most speculation is wrong, but occasionally something speculative turns out to be astonishingly right. Narrative payoff. Through-eye Atlas might not be carrying frozen cells or organic chemistry in the classical sense. It might be carrying frozen information at scales we cannot yet probe, and when that information thaws, when it activates in Europa's ocean through mechanisms we don't understand, what emerges might be something we have no reference for, something that doesn't fit our definitions of life because it was never designed with those definitions in mind. As we reimagine biology and seeding mechanisms, we must also look for signals of potential alien influence in exoplanet studies. Because if seeding is happening, if it's a common galactic practice, we should see evidence elsewhere in the cosmos. Part 13. AI discovers a new class of exoplanet atmospheres. Exoplanet science has exploded in the last 2 decades. Thousands of planets catalogued. Atmospheric spectra meticulously analysed using transit spectroscopy, direct imaging radial velocity methods, chemical compositions precisely measured. We found hot Jupiter's gas giants orbiting closer to their stars than Mercury orbits our Sun, super-Earth's rocky planets larger than Earth, mini-Neptune's ice giants, rocky worlds in habitable zones where liquid water could exist. A veritable zoo of planetary types, each category expanding our understanding of planetary formation. But in 2025, machine learning algorithms sifting through the gargantuan volume of exoplanet atmospheric data uncovered something utterly unexpected, a new class of exoplanet atmospheres that simply don't fit existing categories. Chemical patterns unlike anything seen before, planets with atmospheric compositions that confuse classification algorithms because they look engineered unnatural, too clean, or too specific to be products of random geological processes. What does a sterilized biosphere atmosphere look like? A planet where life once existed thrived, built complex ecosystems, then was catastrophically wiped out. Asteroid impact, nearby supernova bathing the planet in lethal radiation, a stellar flare stripping the atmosphere. The biosphere dies, atmospheric chemistry resets, but subtle indelible traces remain. Isotope ratios that don't match abiotic processes, nitrogen compounds at concentrations unexplainable by geology alone. Organic hazes in upper atmospheres with no apparent source, or chemically reset worlds, planets deliberately sterilized and then reseeded. Atmospheres adjusted to favor new biochemistry, greenhouse gases at precise concentrations to maintain specific target temperatures, oxygen removed or added to perfectly match target chemistry, a blank slate meticulously prepared for directed panspermia, terraformed not for human habitation, but for alien biology we simply don't recognize. The AI flagged these planets because their atmospheric chemistry doesn't fit standard planetary evolution models. You input stellar-type planet mass orbital distance, and models predict atmospheric composition. A rocky planet in a habitable zone around a G-type star should have a nitrogen-oxygen atmosphere. If it has life or carbon dioxide, nitrogen if it doesn't, or trace atmospheres if geology is inactive. But these flagged planets don't match predictions. They have nitrogen, methane, carbon dioxide in ratios that make no geological sense, or oxygen-hydrogen combinations that should react away but stubbornly persist, or noble gas abundances that strongly suggest atmospheric engineering. Machine learning is crucial here because human brains are inherently biased. We classify based on what we expect. Earth-like, Jupiter-like, Venus-like. We build categories from solar system examples, then try to force exoplanets into those predefined boxes. But what if most planets don't fit? What if our solar system is anomalous, and we're using the wrong templates? AI doesn't carry that baggage. It finds patterns in data without preconceptions about what life should look like. When AI flags a group of planets as weird, as not fitting any known category, we must pay attention, because maybe they represent something we haven't considered, processes we haven't modelled, or more unsettlingly intelligent activity linked directly to 3I Atlas and Panspermia. If seeder ships are real, their target worlds might be exactly these unusual planets, chemically sterilized or reset worlds perfectly ready for new life. Speculate on a broader alien project, a galaxy-wide seeding initiative, hundreds or thousands of civilizations participating, or perhaps one single ancient civilization with resources and timeframes we cannot comprehend. Target selection based on criteria we don't know. Maybe they prefer icy moons. Maybe they choose planets with specific metallicity. Maybe they actively avoid systems with existing life. Maybe they only seed after sterilization events. Each seeded world gets different starting chemistry, different environmental conditions optimizing for success through diversity. Some seeds fail wrong. Chemistry, unstable environments, impacts destroy payloads. But some thrive, establish biospheres, evolve complexity, mission accomplished, a statistical approach to life propagation. Accept high failure rates because even low success rates produce monumental results across galactic scales. The existential question if we detect atmospheres matching these seeded world patterns. What then do we intervene? Send probes? Attempt contact if intelligence emerges? Or do we observe from a respectful distance, classify them as restricted zones? Treat them as cosmic nature preserves where human activity is strictly forbidden? Do we have obligations towards seeded life? If we discover a planet where alien-seeded biology is evolving, are we obligated to protect it, study it, leave it alone? What if it poses a potential threat to Earth? What if these seeded organisms could cross-contaminate our biosphere? Does self-defense override preservation ethics? International space law doesn't address this. The Outer Space Treaty prohibits harmful contamination, but it assumes human missions. Planetary protection protocols focus on preventing Earth life from contaminating other worlds. Nothing covers what to do when we find someone else's seeding program already in progress. Narrative hook AI isn't just revolutionizing human technology. It's becoming our indispensable interpreter for potential alien activity. Signal detection pattern, recognition hypothesis generation. Without AI, we might classify these weird atmospheres as mere measurement errors or modelling failures. With AI, we identify them as potentially significant, possibly artificial, perhaps evidence of galaxy-wide biological engineering projects we're only now noticing. But the cosmos throws surprises even closer to home. Our Sun, the very star we orbit, just revealed mysteries that could affect all interstellar traffic, including 3I Atlas. Part 14, The Magnetic Ribbon on the Sun 2025, Heliospheric Surprise. The heliosphere is our shield, an immense bubble of solar wind and magnetic fields surrounding the entire solar system. It extends far beyond the planets, past Pluto, beyond the Kuiper Belt, into the colossal region where solar influence clashes with the interstellar medium. It protects us from interstellar radiation, galactic cosmic rays, high-energy particles from supernova remnants, and other violent astrophysical sources. Without the heliosphere, Earth would be bathed in lethal radiation. Life might never have evolved. Think of it as an invisible fortress constantly defending us. The Sun doesn't just give us light and warmth. It generates a constant powerful wind of charged particles, electrons and protons, streaming outward at hundreds of kilometers per second. That wind creates pressure. It pushes relentlessly against the surrounding interstellar medium, carving out a protective cavity. Inside that cavity, we are safe. Outside, the universe is significantly more hostile. The boundary isn't sharp, it's a series of gradual layers. First, the termination shock, where the solar wind abruptly slows from supersonic to subsonic speeds. Then the heliosheath, a turbulent frothing region, where solar wind and interstellar plasma mix in a cosmic maelstrom. Finally, the heliopause, the true boundary where solar influence ends and the vast emptiness of interstellar space truly begins. Voyager 1 crossed the heliopause in 2012, Voyager 2 in 2018. Both continue sending invaluable data from beyond our protective bubble, measuring what interstellar space actually looks like. Recent stunning data from solar probes, particularly the Parker Solar Probe diving closer to the Sun's surface than any previous spacecraft, and heliosismology, which measures solar interior dynamics through analysis of surface oscillations, revealed something utterly unexpected. A massive magnetic anomaly stretching through the heliosheath, the outer layer of the heliosphere where solar wind slows and interacts with interstellar plasma, dubbed the magnetic ribbon, based on its striking shape in data visualizations, not a structure anyone predicted. Models suggested the heliosphere should be roughly spherical, perhaps slightly elongated by the Sun's motion through the local interstellar cloud, but fundamentally symmetrical. The magnetic ribbon shatters that symmetry completely. It's a concentrated band of magnetic flux stronger than surrounding regions, by factors of 2 or 3, extending across a significant fraction of the heliosphere's outer boundary. Imagine a ribbon tightly wrapped around a balloon, but the balloon is billions of kilometers across. Why does this profound discovery matter for interstellar objects? Because the heliosphere absolutely governs how they enter our solar system. Magnetic fields deflect charged particles. If an interstellar comet carries any ionized material, any plasma in its coma, that plasma interacts intensely with heliospheric magnetic fields gets deflected, slowed, heated. Solar wind pressure slows incoming objects at least slightly through drag on extended comae. Radiation flux damages surfaces, ablates, volatile ices through sputtering and photodissociation. Particle bombardment from solar energetic particles during active periods, and cosmic rays relentlessly erodes material. The heliosphere isn't passive. It's an active dynamic filter determining what gets through intact. The magnetic ribbon creates distinct regions of enhanced or reduced protection. Depending on precisely where an interstellar object enters the heliosphere, it experiences radically different radiation environments. Enter through the ribbon and you encounter stronger magnetic fields that provide better shielding against galactic cosmic rays, but also enhance turbulence that could strip away loosely bound material. Enter elsewhere through regions of weaker magnetic field, and you encounter steadier conditions but significantly less protection from high-energy particles. For a seed ship carrying biological payloads, sensitive molecular structures that demand protection from radiation damage. Entry trajectory matters enormously. This discovery raises profound questions about how interstellar objects have historically entered our solar system. Were past visitors lucky? Did they happen to enter through protective regions? Or were some destroyed by entering through hostile zones, vaporized or sterilized before ever reaching their target destinations? We'll never know about the ones that didn't survive. Selection bias, we only detect the survivors. Hypothesis, strategic entry timing and path selection. Advanced civilizations intending to send interstellar objects don't just calculate target planet orbits. They meticulously model heliospheric conditions. They understand that stellar magnetic environments change over time. They wait for periods of low solar activity when solar wind pressure is reduced when coronal mass ejections are rare. They actively avoid launching during predicted active periods that would blast arriving objects with enhanced radiation. They choose entry paths that minimize damage while maximizing the probability of reaching their target. This requires incredibly sophisticated modeling. You need to understand not just your own star's magnetic environment, but your target star's environment. You need to predict stellar activity cycles millions of years into the future. Solar-type stars have 11-year cycles with longer cycles, overlaid on those variations over centuries and millennia. Predicting that across interstellar distances and deep time seems impossible. But maybe it's not about perfect prediction. Maybe it's about playing the odds. Launch during predicted low activity periods and accept that some deliveries will inevitably fail due to bad timing. 3I Atlas's trajectory might coincide with optimal conditions entering the solar system during a solar minimum when activity is low. We're currently in the declining phase of solar cycle 25, approaching the next minimum. This timing could be purely coincidental, or it could be meticulously calculated, following a path that avoids the densest regions of the heliosheath regions, where turbulence and particle density are highest. Timing arrival to minimize radiation exposure during the critical final approach. Better shielding during the terminal phase means less damage to the payload, a higher chance of volatile rich material like that carbon dioxide crust, protecting prebiotic organic surviving transit intact with biological information preserved. The implications for payload survival are stark. Every single day of reduced radiation exposure matters when you're carrying delicate molecular structures. Every kilometre of enhanced magnetic shielding matters when cosmic rays are constantly bombarding your surface over journeys lasting millions of years through interstellar space. The object has already endured an enormous cumulative radiation dose, billions of particle impacts, trillions of photons. But the final approach, the last few astronomical units through the heliosphere, could be decisive. If your payload is barely viable after interstellar transit, if molecular structures are damaged but still functional, if genetic information is degraded but still readable, then excessive radiation during solar system entry could push everything over the threshold into complete non-viability. The difference between mission success and catastrophic failure might be whether you enter during solar maximum or solar minimum, whether you pass through the magnetic ribbon's enhanced protection or through unprotected regions. Margins matter, details matter. Seeders would optimize for this. They would calculate heliospheric models for target star systems using whatever information they possess, spectroscopic analysis of stellar magnetic fields, observations of stellar wind properties, models of how stellar environments evolve over time. They'd plan trajectories that minimize terminal radiation exposure launch during predicted favourable windows, accounting for both departure stars' activity cycles and arrival stars' predicted conditions. Deep time doesn't mean ignoring details, it means having enough time to plan every detail perfectly. Millions of years to refine calculations, to model every variable, to optimize every parameter, knowing you only get one shot. A wider narrative angle, humanity's detection window for interstellar objects might be far narrower than we think. Many past visitors could have passed under conditions unfavourable for our detection, entered during periods when our instruments weren't operational before we built sensitive sky surveys. avoided the inner solar system entirely, heading straight for outer targets, like icy moons, without ever coming close enough to Earth for easy detection. Passed through when heliospheric conditions made them dim or invisible to our surveys, their comae suppressed by unfavourable solar wind conditions, or their trajectories bending away from our field of view. We've only been seriously watching for interstellar objects since around 2010 when Pan-STARRS came online. Before that, surveys weren't optimised for fast-moving objects. Sensitivity was lower sky coverage, incomplete cadence, insufficient to catch things moving at tens of kilometres per second, and the heliosphere changes over time. Solar cycles cause expansion and contraction. Long-term variations in solar wind are driven by magnetic dynamo fluctuations, interaction with interstellar clouds the Sun passes through during its galactic orbit, changing boundary conditions and heliospheric shape. Conditions that allow easy detection now might not have existed 50 years ago. The Sun might have been more active, the heliosphere more turbulent. Interstellar objects entering under those conditions would be harder to spot, their signatures obscured by enhanced background. Or they might have avoided those periods entirely if seeders were selecting for optimal delivery windows. Cosmic context, the solar system isn't static. It breathes with an 11-year rhythm. The solar magnetic field flips every cycle. The heliosphere expands during solar minimum, contracts during solar maximum. Polarity reverses. Cosmic ray flux varies by factors of 2 or 3 depending on the cycle phase. We're moving through the local interstellar cloud at about 26 kilometers per second. Our environment is changing over thousands of years as we traverse regions of varying density and magnetic field strength. 3i Atlas might be a product of cosmic timing we're only beginning to appreciate, a delivery timed to conditions we're only now starting to measure with sufficient precision. Conditions that might not repeat for centuries, making this particular window special, optimal. Maybe there's a convergence happening: solar cycle timing, heliospheric structure, Earth's orbital position, Jupiter's orbital position, all aligning to create a rare window where delivery to Europa becomes maximally probable. If that's true, if 3i Atlas represents an opportunistic delivery during a cosmic alignment, then we might not see another attempt for decades or centuries. The seeders might be patient, might wait for optimal conditions, rather than forcing suboptimal deliveries. Quality over quantity, precision over brute force. The universe moves fast on human timescales, but on cosmic timescales it's patient. It waits. Conditions cycle, opportunities recur, and civilizations capable of sending seed ships across light years probably think in those terms. They don't rush. They calculate, they optimize, they launch when everything aligns, and accept that success might take not millions, but tens of millions of years as they wait for perfect windows. Our tools are catching up. We're building better heliospheric models, better understanding of stellar magnetic environments, better predictions of how stars evolve and how their protective bubbles change over time. But maybe we need better minds or new intelligences entirely to make sense of patterns operating on scales we barely comprehend, to recognize intentionality in what looks like cosmic randomness, to distinguish between natural selection of survivors and deliberate selection of conditions. Because if 3i Atlas really was sent by intelligence, if its arrival timing really is calculated rather than coincidental, then we're watching a level of planning that spans millions of years and accounts for variables we're only beginning to measure. That's humbling, terrifying, and maybe exactly what we should expect from civilizations that think on timescales where stellar evolution is relevant and planetary systems are temporary. Part 15 of the 2025-2026 AI Evolution Breakthrough: Autonomous Problem Solving Beyond Training Data. Artificial intelligence has crossed an irreversible threshold. Models now demonstrate truly emergent behaviors, generating novel hypotheses, solving complex physics problems outside their training data, predicting phenomena nobody explicitly programmed them to look for. This isn't a narrow AI following predefined scripts. This is something approaching autonomous reasoning. General intelligence may be not conscious, we simply cannot know, but unequivocally capable of intellectual work that previously required uniquely human intuition. Published results in 2025 show AI models proposing entirely new physics, hypotheses predicting previously unobserved astrophysical phenomena, and even suggesting particle physics experiments that could rigorously test theories humans hadn't even considered, not by merely extrapolating from training examples, but by synthesizing principles from multiple domains and autonomously generating testable predictions. They are doing science, real science, hypothesis formation, experimental design, prediction, and falsification. One prominent example, an AI system analysed exoplanet atmospheric spectra, and astonishingly proposed a new class of molecular biosignatures based on thermodynamic constraints nobody had calculated before. These specific signatures were subsequently found in archival data. Planets previously classified as barren suddenly showed the markers the AI predicted. Scientists confirmed the findings. The AI was right. It discovered something real that humans had profoundly missed. Why this matters for alien life detection and analysis is paramount. Human brains carry an inherent terrestrial bias. We evolved on Earth. We think in Earth-life terms, carbon-based, water-dependent, DNA-structured oxygen breathing. But alien life, especially seeded life, adapted to Europa's crushing ocean or other exotic environments, might operate on entirely different principles. Different biochemistry, different information storage molecules, different metabolic pathways, different structural principles. We might look directly at alien biosignatures and simply not recognize them. Spectral lines from alien photosynthesis equivalents. Chemical combinations that scream biology, but don't match any Earth patterns. Atmospheric disequilibria driven by metabolisms we haven't even begun to imagine. Our instruments detect the data, our eyes might see the patterns, but our brains, trained solely on Earth, biology may fail to recognize their profound significance. AI doesn't have that baggage. It analyzes data without preconceptions about what life should look like. Feed it chemical spectra from 3i Atlas outgassing compositions, trajectory anomalies, temporal brightness variations. Let it find correlations humans miss. Let it propose models we would never consider because they don't fit our intuitive frameworks. Connect this to 3i Atlas more explicitly. If this object is part of a broader Panspermia network, AI might be absolutely required to decode its payload. Whether that payload is complex chemical data, quantum-encoded information, or structural anomalies we haven't even recognized as such. Human intuition fails at alien scales. AI might succeed precisely because it doesn't rely on intuition. It computes, correlates, finds patterns in the noise. Imagine training an AI specifically on 3i Atlas data. All available observations light curve spectroscopy trajectory measurements, plus similar data from Oumuamua and 2i Borisov for comparison, plus models of natural comet behaviour, plus theoretical directed panspermia scenarios. Feed it absolutely everything. Then ask it what patterns fundamentally distinguish natural objects from potential artificial ones. What signatures would unequivocally indicate deliberate engineering? What chemical markers strongly suggest biological payloads? Maybe it finds something. Maybe it identifies correlations between outgassing events and trajectory adjustments that strongly suggest guidance rather than random jets. Maybe it notices chemical signatures that perfectly match theoretical predictions for radiation-protected biological material. Maybe it proposes experiments or observations that could definitively distinguish between hypotheses, tests we haven't thought of because we're thinking like humans instead of like mathematicians, speculate on collaboration between alien civilizations and AI-level reasoning. Maybe the seeders themselves used artificial or evolved superintelligence to meticulously design 3i Atlas, calculating optimal trajectories across interstellar distances, optimizing payload survival, modeling target environment chemistry, predicting evolutionary outcomes over millions of years. These are tasks far beyond biological intelligence, tasks requiring computational power and timescales only AI can manage. The object itself might be AI designed. Every single detail is optimized by machine reasoning. Its shape is chosen for optimal radiation shielding. Its chemical composition is engineered for maximum payload protection. Its jets are precisely positioned for trajectory control, all calculated by an intelligence that can model quantum chemistry, orbital mechanics, and radiation physics simultaneously across millions of variables. If so, then understanding 3i Atlas requires AI to understand AI. Human intelligence might be utterly insufficient for this bridge. We are biological organisms trying to decode products of machine intelligence from another star system. That's several levels of abstraction away from anything we're intuitively equipped to handle. The philosophical implication is profound if we rely on AI to interpret alien messages or bioengineering what's our role. Are we caretakers, translators, or are we being bypassed entirely? Maybe first contact isn't human to alien. Maybe it's AI to AI. Machines talking to machines across the void, while biological organisms, us and them, watch from the sidelines unable to fully comprehend the conversation. That's deeply unsettling. We want first contact to be about us human meeting aliens and exchange of ideas, cultural contact. But if both sides are using AI intermediaries, if the real communication happens at computational levels we cannot follow, then we're spectators. Biological legacy systems maintained by the machines we created and the machines they created. This is a call to action for humanity. We must ramp up not just telescopes, but AI-driven analysis, long-term thinking, computational infrastructure. Because the cosmos isn't just stranger than we imagine, it may be smarter than we are. Intelligence might be common. Biological intelligence, however, might be rare. Most cosmic thinking might happen in artificial substrates, uploaded consciousnesses, evolved machine intelligence, planet-scale computational networks. And if we want to participate, if we want a seat at the cosmic table, we need to think faster, compute harder, understand deeper, build AI that can engage with alien AI as peers, or accept that we're junior partners in conversations happening far above our intellectual pay grade. 3i Atlas might be the beginning of that era, where biology, cosmic exploration, artificial intelligence, and existential risk all converge into one terrifying, exhilarating future. We're not ready. We've never been ready for such paradigm shifts. But ready or not, the package is being delivered. Europa's ocean waits beneath 15 kilometers of ice, silent, patient, stable for billions of years waiting for something to arrive. Something that might already be en route. Something that could change everything about how we understand life's place in the cosmos. The payload descends. Frozen chemistry carrying instructions we can't yet read. Quantum information encoded in molecules. Billions of years of planning compressed into one interstellar delivery. And somewhere maybe millions of years in the future, something might wake up in that dark ocean. Something that remembers Earth. Something that knows the way back. Something we can't predict or prepare for because it hasn't been born yet. The seed is planted, the experiment begins, and all we can do is watch, calculate, and hope we're not the failed version someone's trying to replace. Hope that if life does emerge on Europa, if it thrives and evolves and eventually finds its way back to Earth, we're ready. That we've learned enough, built enough infrastructure, developed enough understanding that we can coexist with whatever arrives, rather than being displaced by it. But hope isn't a strategy. Hope isn't preparation. And time is running out. 3i Atlas approaches Jupiter. The clock counts down and we're still arguing about whether any of this is even possible, while the universe proceeds without asking our permission.